Hello, hello. Can you guys hear me?
Yep.
Yes.
All right. Okay. So today, Arun and I will be presenting on modern shellcode. Basically, it's almost the same thing as normal shellcode, just that we are trying to show more of the 64-bit variants of it, because most of it used to be 32-bit. So here we go. Okay. To start off, we'll just give you an introduction or the so-called the basic case. After that, we will present you with some prerequisite knowledge so that we can try to fight against the common mitigations. Then after that, we will go through the most painful mitigation there is, which is the SecComp filters. Okay, so basically your shellcode is just, basically all shellcoding challenges are just your binary will allocate a region of memory, either through mmap like this, or sometimes it will just create it in the heap via malloc. Then it will change the protection to read, write, exec. So after it does that, that region of memory, you can reformat, write to it. Also, you can run it as executable. So once you have such a region of memory, right, usually the program will let you read into it like this. Sometimes there'll be some length limitations. Sometimes there'll be some character limitations. So after it checks through all those kind of limitations, right, it will just run the code for you. Then your aim as the challenger, right, is you're supposed to get shell, or you're supposed to be getting the flag. Usually getting shell is a surefire way to getting flag. And this is why shell code is supposed to be an important part of on. So basically, yeah, this is our overview, and this is what our aim is. So let me just, all right. So once you see the challenge, right, the first thing you will do is where to get shellcode from. So just searching it up online, x64 shellcode, you will already see a few answers here. Then you could just copy paste it and it will work. So here's the code that I was talking about before. And here is the solution for it based on the Googleable solution.
Can zoom in a bit. 1 or 2 times. Easier to see.
How to zoom in?
Control plus. No? Okay.
Oh, all right. It's very unresponsive. But I think okay, this is okay, right? Okay, moving on. Okay. So now I'm just going to solve the pi. Okay. I attach it to a debugger so that you guys can see like how the code is being executed. So over here is your disassembly. Right now we are at read. We are paused at read. This is your stack. This is your backtrace. Then I'll show you the registers whenever it's important now. So right now we're here, right? We want to go to the part where our code gets executed. And since our code gets executed somewhere in main, right? So here's our create, here's our read, here we check for validation, and this is our part where we literally execute a code. So let's go to this part. Let's set a breakpoint in this part. Then let's continue execution. Okay, you can see that the next instruction to be called is our shellcode, which is at this address. So let's step once. All right. So maybe this is not very useful. I'll show you this. Also not useful. Back to this. Okay, so this here this is our shellcode editor's address. So you can see that we have some instructions here. Then after that, we have syscall here. After that, just add byte. This is basically your 000000. That's all. So let's step through what our shellcode does. So the first thing it does is XOR RSI, which means setting your RSI to 0. Okay. So now you can see that your RSI is 0. Then after that, the push here means you're pushing the register, the value of the register to the stack. So just watch the stack here. Okay. Now you can see that RSI, which is 0, is being pushed over here. After that, we are going to move. Move abs means move an absolute value. In this case, this string here is actually bin sh. Yeah, okay, but it's in reverse because your numbers, sorry, when your instructions are stored in the other way around. But this, when your computer reads it as a string, right, you'll go the other way. Okay, after that, you see a push RDI. Then you see a push RDP. Sorry, push RSP. Then we pop RDI. Reason we pop RDI here is because we push RSP, then we pop RDI, right? Now RDI is equals to RSP, which maybe after, yeah. You see here RSP is this value. You will see here RDI is this value. Then we push this constant, then we pop it. So this two basically just do the same thing as setting RSI, sorry, same thing as setting RAX to 0x3b. And now your RX is 0x3b. CDQ, okay, I don't want to explain this very much, but CDQ is basically you are copying over your RAX to EDX and EAX, splitting the two and then setting the two registers at the same time. Not important, we'll never see this instruction ever again, just for curiosity's sake. So after that, we have our syscall. So here my debugger just helpfully says it's exec and the string is bin sh. Then if we continue execution, you'll see that over here, I have a shell. Yeah, so this is basically your layout for shellcode challenges. So now I will go through Arun will go through some prerequisite stuff that you should know so that we can further expand and teach you more about shellcoding. Arun?
Yep, sure, thanks, Akash. Can you guys hear me?
Yep.
All right, great. Okay, so we'll just go through what assembly languages first of all. So in very simple terms, it's the last frontier between software and hardware. So here we can see examples of the move command, where move copies a value from the source to destination. So basically, the assembly language is based on processor architecture, and there are mainly 4 types. You guys might have heard of it: CISC, RISC, DSP, and VLIW. So CISC is used in x86 architecture, and it's more complicated than RISC. So RISC attempts to make the most common operations faster through complex and efficient instructions. A few examples of this difference is shown in the picture below, where x86 uses CISC and ARM uses RISC architecture. So ARM encodes its instructions into opcodes of a fixed length of 4 bits. However, the length of encoded instruction varies for x86 from anywhere between 1 to 15 bits. The same move instruction has multiple encodings as shown in the demo next. I think Akash should be doing the demo now. Yep, I think this should be it. Okay, yeah, so that was pretty much it. As you can see, there was different move commands there of different lengths. So I think we can go on from there to the next slide, registers. Yep, so next, let's just have a quick look through what registers are. So registers are just a location that is quickly accessible to a computer CPU and usually consists of a small amount of fast storage. Nearly all computers load data from main memory into registers in order to perform computations or manipulations. For example, adding, subtracting, jumping, and comparing. And this is specified by the computer's instruction set architecture. Some major accessible registers are your general purpose registers, shown on the left of the picture there. And then the special purpose registers and also program counter. So the user can access the general purpose registers and change them. It can also include operand data or addresses. Special purpose registers, for this, the users can't directly access such types of registers because they are for the processor itself. For example, special registers can hold program counter, which is responsible for addressing commands for processing. And finally, the program counter, the register is responsible for keeping the address of the next command in the main memory to be processed. And normally after every command, the number 1 is added to indicate the next address location. As you can see that the floating point XMM registers were introduced with SSE and is 128-bit wide with instructions that can treat them as arrays of 64, 32 or other bit values. So virtually all the floating point math is done through these XMM registers. So yeah, that's pretty much it for registers. If that's fine, then we can go on to the stack. Great, so I think most of you guys would have been familiar with this from our modules here in NUS. So the stack frame is just a collection of all the data on the stack associated with one subprogram call. It resides at the high end of the memory and goes downwards or upwards depending on whether the stack is implemented in a descending or ascending fashion. So we interact with the stack using a push and pop instruction. And this stack frame generally includes the following components, which are the return address, argument variables passed to the stack, local variables, and saved copies of any registers modified by the subprogram that needs to be restored. So in this example, we can see the two registers, RBP and RSP. So RBP, known as a base pointer, contains the memory address of the base of the current stack frame. RSP, also which is the stack pointer, contains the memory address of the top of the stack. And the stack pointer will change when a subprogram does a push or pop operation. So I think these two will be, we'll come back to it later on in the demos. And then we can go to the next one, syscall. Yep, okay, so finally syscall. This is just how a program enters the kernel to perform some task. So programs use system calls to perform a variety of operations, such as creating processes, doing network and file input-output, and much more. You can find a list of system calls by just checking the manual page for it. User programs, I'm gonna show it. Yeah, sure.
Yeah. Okay, so this is all your list of syscalls here. Then, for example, to do the read syscall, right, you have to set REX to 0, and RDI to your file descriptor, RSI to your buffer, and so on. So there's actually
A lot.
a lot. And this is not even the most updated one. So yeah.
So you can always take a look there and you can check it out later on too. So right now, okay, so I'll just go on. So user programs like our editor, terminal, SSH daemon and stuff, they need to interact with the Linux kernel so that the kernel can perform a set of operations on behalf of the user programs. Because they can't perform those themselves. So for example, if a user program needs to do some sort of input-output or modify its address space, it must trigger the kernel to run to complete those actions on its behalf. So what we might think, like what prevents user programs from performing these actions themselves is just because of this concept called privilege levels. So it's just a means of access control, and the current privilege level determines which CPU instructions may be performed. So the kernel runs at the most privileged level, while user programs run at a lesser level. So in order for a user program to perform some of these privileged operations, it must cause a privilege level change so that the kernel can execute. And that is the reason why we have the system calls. I think, yeah, that's pretty much it for the background information required for the next portion.
Test. Okay, so shellcode is basically you're using all of the knowledge you learned before, your assembly, syscalls, register and stack, and your aim is just to do to call the instruction called syscall with your REX set to 59, your RDI set to bin sh, your RSI set to null usually, and your RDX usually set to null. This is because we are trying to fit our assembly code to do the equivalent of this. So you want this to be as null as far as possible because it doesn't matter, and this also to be null. So that's the point of this. So since we can, since the earlier shellcode I showed does this, right? Can you guys try to like work out shellcode that does open? Okay, let me type it out. Open flag.txt read. I'm just gonna say RSI. Yeah. Okay. Can you guys try to write some assembly that does the equivalent of this? I'll give you guys like 10 minutes. You guys can either type in the chat, I'll just type it out here, or you can unmute and say it, and also type it out here for you. So you try to use the cisco table that I showed just now, and also try to like think of some common assembly examples. It's okay if you guys are a bit wrong, as long as your general gist is correct. I'll try to correct you guys as you go. So how about I give you guys 10 minutes, then you guys try to work out to do the equivalent of this.
Paste the cisco table somewhere.
Okay, guys, how's it going? Any progress other than Zor RDX RDX? You guys?
This one is for we are talking about open now, right?
Yeah, just
Just open. Okay, right, I'll put mine in the chat. This one, I go type it somewhere else first.
Mm, Yep. So Daniel's one for no, no need. Actually, you can just set RSI because your mode flags, sorry, your mode and flags for the table, right?
Yeah.
Who's it?
What about them?
Your open, right? So this must be your one, which you set correctly. This and this can be 0 and 0. Flag 0 is your default value, which is just read. Mode is also 0. I think it's O create, sorry, O read or something like that, which is 0. So you just XOR these two.
Oh, okay.
Okay, so that's a bit less pain. So after that, okay, since we are actually taking lessons, all right, I will just write it over here. So this is almost the same thing as what you did, except I think it's a bit wrong because I did 2 pushes with this. Okay, so otherwise, yeah, this is wrong. This is wrong. But let me just type the correct part here for read. Okay, read, we have to set your Rx to 0. You have to set your RDI to whatever file descriptor. So after your open is done, right? The open will give your return value, which is the file descriptor, inside your RAX. So this is a x64 calling convention. Your return variable, so your return value is returned to RAX. So now you have to give this RAX to be your return value of open, which contains your new file descriptor. You just save it into RDI because later on you'll be using RDI for this. Then after that, your RSI, which is whatever buffer. I just said you guys can use whatever buffer you want, right? So just RSI low. Then RDX would be the whatever constant for some length. RDX will be 0, then cisco. So this will read from the file flag.txt and it will just write in the buffer. So, but you want to see what's coming out of the buffer. So let's set RDI to 1, because 1 is your standard output file descriptor. Let's set RSI to RSI is just RSI low since your output buffer is already there. Then the length, which is RDX, it just says some length. After that, we follow the cisco table. Right is cisco number 1. Then invoke cisco. And this is your trick that we can call the ORW, which is open, read, and write. This is especially useful since sometimes exit read is blocked. And I'll talk more about that when we come to second. So anyway, moving on. Okay, so some general tips when you don't have protections, right? When you don't have any common mitigations and all that, right? Sometimes there'll be some funny length limitation, like you have to give like shortest shellcode. And the 23-byte shellcode I just gave is actually one of the shorter ones. But let's say you want to try to make it short, even shorter. You can do some tricks like instead of doing move REX 0, right? Just XOR whatever register it is with itself. Because if you XOR a value with itself, it will give 0. Because XOR depends on whether or not the value is same. So since you're sending the same value, your output will be 0. After that, you have stuff like multiply. So if you multiply by a constant base, right, just do shift left. This is way shorter in memory. Sorry, way shorter in terms of opcodes. Then, okay, so when sometimes you write shellcode, right, you will come upon this thing where all of your shellcode, at the end of your shellcode, you just see this instruction, add by pointer, REX, AL. The reason why you'll see this over and over again is because that's encoding for 0, 0, 0, 0, 0, 0, 0, 0. If you have since just all null bytes, right, it's a valid instruction. It's actually a valid instruction, which is this one. So if you come upon this and you don't want to make your program seg fault or crash or anything, right? You want to try to bring this into a norm, which is by making this a valid thing that a valid pointer. Because this is it's trying to interpret Rx as a byte pointer here, right? So just set Rx to some value that is valid in memory. Then as long as you don't care about where it's pointing to, it should be okay. So those are some general tips for you when you do some shell coding. Okay, actually I did this. So I'm going to skip this actually. Okay, so here will be our first mitigation, which is just stripping out white space. So here's our code that we helpfully copy pasted from shellcode.com, sorry, exploitdb.com. So here's the same shellcode when you print it out in your console. The thing is, if you can see here, there are no white spaces. And this is actually a pretty good thing about shellcode is you usually, if you encode, sorry, if you're smart enough, and this guy is really smart, the one who made it, I mean, for me, he will usually do stuff like XOR RX instead of doing loop RX0. Because this one will include null bytes in it. And this guy doesn't do this kind of stuff. So when it comes upon this, it'll actually escape this white space. There'll be no issue. So next will be some thing where your program will filter out unprintable characters. So let's see over here. Our shellcode is H1, sorry, H, then 1. Then this here is one character. And it's F6. F6 is not really a valid character, like not a printable character, which is why in the first place your console gives it out as like this. So once it comes upon not print right, it will just exit and it will count it as not valid. So what can we do when we come upon this kind of problems? So what our printable, we can consider printable characters are actually a lot of different characters. So what we want to try to do is like try to search for something similar to printable characters. In our case, would be just this thing called alphanumeric shellcode. So just searching online, I've already one result. And there's a direct code for it. Sorry, 87 bytes. So pasting it, it will work. But let's say for CTFs, right? Especially for CTFs, right? You have this weird kind of questions where, oh, I'm only allowing you to enter opcodes between 00 and 0xf, which is kind of a strange thing to ask, but they do ask it. So when you look at these kind of problems, right, you have to think on how you have to approach it. The first thing you can do is be an assembly god and actually read the Intel Developers Manual, which is 2,000 pages long. But let's say we don't want to do that because we are not gods, we are just men, and we have this. We just try to generate, because our character set is actually quite small, it's just 15 characters, sorry, 16 characters. We just do 16 to the power of, okay, by right, the max number of characters, max number of outputs for instruction is 15. But we can try to like aim lower. Let's just go for 5 characters. So all possible outputs of length 5. For example, 00, 00, 00, 00, 00. That's all. So we can try to generate all of this, then run it through a disassembler and see if they are valid. So this script here, right? I've been using it for the last, I don't know, 4 years. It has never once really failed me. Like, it's just a very, very good reusable script. I found online, I just keep using it over and again. All I have to do every time is just change the char set a bit to change the value characters. After that, I just run it and you can see output like this, where you can show all the value instructions. So once you have something like this, right, what you optimally want to do is you try to scroll through it and you just try to find some patterns. So here you can see add byte pointer, RX plus RX, add byte pointer, R6 plus R6. Then just like scroll down a bit, try to, or you can see, you can modify AL directly here, or if all instruction for some reason. But the rest of it here, they look largely useless. This kind of instructions can only be used in kernel mode, so not our problem. So IMO, the most important things that you can find are like these instructions and stuff over here, where you can like change the value of AL or change the value of CL. So for this gel coding challenge, gel code challenge, yeah, I don't have my code for it anymore, but I'll just run through the explanation for it. Basically, you just try to like, RCX will be 0 already when you jump into the part. So what I did was I controlled AL using all these instructions. Then I believe yes, RDX. RDX is the location of your shellcode. So what you do is, using your limited shellcode, which is usually just this, then you try to modify your AL, and you try to modify your CL, right? This is like an array indexing operation. So what you can do is, you just try to write, using your shellcode, you write even more shellcode. You write it byte by byte, since you have a byte pointer here. So to vary the shellcode you write, right? Just change AL. So for example, if I want to write the opcode for cisco, which is 0x0, this, right? I will increase AL by, I will increase AL by 9, then I'll increase AL by 6 after that, and we have F, 0xF, which is 15. After that, I will just write it. I will run this instruction so I can just type it out. Like, I can just like write it into another piece of memory. Same thing for this. If you want to, because this is add AL, right? So it will overflow at 256. So you just add until it overflows and becomes 5, and then after that we just add here. You're assuming that the byte pointer pointed by this is already 0, of course. And yeah, that's what I remember on how I solved this challenge specifically. Okay, so here are some general techniques that usually end up using whenever you come for shell coding challenges. So the first thing you do, will be, of course, this one. Try to generate all the possible shell codes. You look through it, trying to find some patterns. So yeah, try to find some patterns like this. Then what you have to do is like try to think how you can fit those patterns and generate one of these ideas. So the first one will be this thing called two-stage payload. So two-stage payload is basically like let's say there's some restriction on what shellcode you can initially initially run, right? Just try to like run the read. You just try to run read. You have your first stage will just be trying to get the read syscall to work. So you try to get the read syscall to work, and you read in more shellcode. But this time there are no input restrictions because the read is controlled by you. You choose what to read. So once you read in more shellcode, right, you have to jump to that shellcode, and that will give you exit read. So that's one way to defeat this kind of character limitations. Then the other one is the arbitrary write byte primitive, which is exactly what this is. Using this, we write any byte we want to any location we want. But you just have to make sure that you can jump to the location afterwards. So either you use precise calculations, or you have to make sure that you have a read, call, jump, any of these kind of instructions around that can be used. Another one is this thing called encoder heads. So this is the case where, let's say you really don't know for printable characters, right? let's say instead of printable characters, you have base64, but you really don't want to figure out how to write base64 shellcode. So what you can do is there are some pre-existing base64 shellcode, base64 code that will just decode other text, then it will try to run that text. So you just try to provide a base64 encoded version of your shellcode to that kind of code. They will do it for you. And this method is called encoder heads. Then there's the last one, which is the most painful one, which is called self-modifying, because as you execute, self-modifying instructions will either change, like the next instructions are immediately running or the previous instruction that was running. And this is very hard to do because you really don't want to come across a scenario where it tries to write the instruction that you're currently currently executing. This will just cause a crash, and it's very hard to debug. Okay, so next, moving on, we will move on to the most painful mitigation for shellcoding, which is SecComp. SecComp just stands for secure computing. And the way that it works is you try to describe a sort of a program written in this language called ebpf, where given your arc, your syscall number, right, it will go through a list of conditions, then it will either return to allow the syscall or to kill the syscall. So the code for this it's kind of painful. There are some tools, however, for SecComp tools, where it will run the program, it will try to extract the ebpf rules, the SecComp rules rather, so that it isn't very painful for you guys. It will show you in this nice format here. So based on that, right, for example, this one, A equals arc, okay? So if the arc is not your 64-bit, it will go to 10, and 10 is kill. Okay, next line. You get a syscall number. The syscall number is below this number, go to 5, which is when you check whether it's read or write or open. And all of these go to 009, right? And 009 is allow. So this one means you can read, write, or open. But if you see here, exit, not equals exit, go to 10. So only this, and this also. Because if it's not equals exit, it will go to 10 still. Only these 4 syscalls are allowed. So ebpf will describe this kind of code, and it will be evaluated in the kernel actually. So kind of a off-topic thing. There's actually some people who managed to exploit the kernel through custom ebpf programs. But okay, out of topic. Back to our original topic. So anyway, so usually what it will do is it will try to block stuff like exit read and other stuff, but it will let read, open, close, all this allowed. So right? Is allowed. So you can't get shell, but you can get open, read, and write. So this is the normal thing, the normal solution that we will do. But let's say like read is blocked. The other thing you can do is you can use mmap. Mmap to like memory map the file into your memory, and then you can by David and try to like get this to work. Another thing is actually if you look into your syscall table, right, there's a lot of syscalls that do similar things to read. So you have pread, read, okay, this doesn't matter. Read ahead. Yeah. This is basically your vector read, where you can do this and you read to vector read is like supposed to be a faster read or something. I'm not really sure myself, but it can read a file. Same thing for this. Yeah. So there's whatever Cisco you can think of, right? There's already some alternatives. Even execve, right? If you see execve here, there's one more version of it called execve at. And if you think about it, actually this like ebpf is just a program, right? And programs can be fooled because they're made by humans. So is this thing here, it doesn't like check against a family of execve. It doesn't check against execve and friends. It will only check against execve. It will only check against execve's syscall number to be specific. So it can be fooled to a certain extent. So the other thing here is, okay, let's say here, right, we block open add, execve, we block clone and fork, because clone and fork, you can use it to open up another process where the SecCom rules may not be applied. So that's a tip. If you guys don't, sometimes the PR control and SecCom setup, right, is very flawed, then you can use this sometimes, but not always. Anyway, so you can see here that all our shell friends are blocked, but even our open as necessary is blocked. So what we're going to do here is, notice here that we only check against Cisco numbers, but here we check against arc. So there's this technique that uses this instruction called redf. It switches between 64-bit and 32-bit execution. So if you guys use Windows, you guys definitely heard of something called wow64, which basically switches between 64. So that's the same thing as this basically, but that one is like controlled in the user mode, controlled by the kernel. But this one is like directly supported by Linux and can be used by the user. So basically, you're allocating a memory, region of memory here. In this address, just make sure it's within your 32-bit address space, like can be accessible by ESI, EDI, EAX, stuff like that. Then you read into this buffer. You read like 32-bit shellcode, actual 32-bit shellcode, not 64-bit, must be 32-bit since you're changing modes. Then this invocation here is the way to read redf. So what redf basically does is it pops two values from the stacks. So usually redf only pops one value, which is your just return value, and just jump into it. But redf will pop two values. The first one will be your actual return address, and your second one will be this value called the CS register. So your 64-bit execution, right? Your CS register is usually 0x33. That's 64-bit. For 32-bit, it will be 0x23. So if you provide this here, right, it will jump to our location, which is this. It also happens to be the location of our shellcode, and it will start executing in 32-bit mode. So, okay, let me show you guys. From the get-go, already stuff is looking very different. Like 0 is weak here, right? But 0 is cisco, sorry, reset cisco here. Then for 32-bit, 5 is open, but for us, 2 is open. So since your syscall numbers are different, right? And your syscall filter will check only by the syscall number, and that syscall number is your 64-bit syscall number, right? You can basically fool your SecCom into thinking that you're doing a different syscall. So if you do open, for example, you will think that your open, which is number 5, will be fstat. You will think that you're doing fstat. And since fstat is allowed, there's no problem. Okay. So actually, wow, we already used 1 hour. Yes, I was talking a bit too fast. So, okay, shellcoding is not exactly the easiest thing to do. because it requires that you have good debugging skills and good knowledge about assembly and like how to like at least like how to set registers yourself, how the stack works and all that stuff. But there are some aspects of shellcoding where you can just like brute force it, then use your existing knowledge to solve challenges. Like the things about instead of knowing like all the instructions in the Intel PDF, right? You just have to know a small subset, and you just brute force that subset and keep using the subset over and over again. And that's exactly what shellcoding is really about. It's about choosing which instructions to use and which ones are like you can just like skip over. Which one is considered to be a no-op. And that's about it for my presentation here today, guys. So is there any burning questions that you guys want to ask? Or do you guys want to make challenges? Like right now for you guys?
You make challenges?
You want shellcode challenges? I will bully you with shellcode challenges.
You can make it for our CTF.
Later on. Okay, yeah, that's about it. Is there again any questions for me, guys? Any questions for Arun also? I think you just wait 5 minutes first.
Okay. Oh, just now you mentioned the encoders, right?
Yeah.
You have any nice recommendations?
For 32-bit, there's quite a lot. If you just Google search it, 32-bit is very common. But 64-bit, I have almost no recommendation. They are all trash.
Okay.
Yeah, it's kind of fun. I think I should probably go and like experiment. There must be a reason why not a lot of them exist. There must be a reason. It's very suspicious that 32-bit is supported, but 64-bit is not. How do I get good at PON? So there is this Intel PDF right over here where all the instructions exist. Go ahead and memorize it. Okay, kidding. Just go do more Pico CTF law. Pico CTF. Then you can see instructions like these. My God, my eyes. But it's pretty fun now. There's a lot of weird stuff to see. Then I have like, these are basically what you can call variable outputs. For example, oh no, this one is results. Please. Yeah. Can use high NB Python notebooks. Pretty good. Okay, wow. Where is me? Oh, yes. Yeah. So if you guys don't know what it means to have Rex, Rex is like it's a prefix that says switch mode to use like, let's say you're in 32-bit mode, right? Your times 2 your register size. So in 64-bit mode, it doesn't really do much. But what is your favorite SSC ASM instruction? Wait, let me go find it. BP. Yes. Yes. You like the sound of this? This is good instructions. This is basically your vectorized matrix multiplication, I think. P sharp D. Oh, what is this? Wait, shuffle. Yeah, is it even, it's not even like randomized, right? It's like a typical shuffle, just wow.
The thing is you can give the order to shuffle in. 'Cause there was
Oh, like okay, okay, okay. I
it
see.
was in the DSO CTF.
Look
in
at that.
the
The
Android
CTF
challenge.
that no one really, I'm sorry, I never really saw. This. Okay, anyway, if you guys have no other relevant questions about Shellcode, I think can end. Danielle?
Okay. Thank you. Thanks, Prof.
Nope. Bye boy. Bye guys.
Wait. We have to try this. Someone needs to say, don't forget to like and subscribe.
Hey guys, don't forget to like and subscribe. Please do
Okay.
subscribe. We do get money after this after all. Aha!
Yeah, the money comes into my account. Maybe. Okay, I end the recording now.
Alright. Bye guys.
Bye.